Problem 289, Game of Life. This is the famous Game of Life by John Conway, British mathematician John Conway, who apparently designed this game in 1970. Now, this game is a zero-player game. Once initial state is supplied into the game, no input is needed from a player. So you can't really play this game other than thinking, coming up with interesting initial states. And depending on the initial state, when the game plays itself, the board can come alive in interesting ways, right? You can see as if some sort of complex creatures arise on the board and they straddle the board, walk across the board, and sometimes bump into other creatures and they fight for resources. That is, if you have vivid enough imagination, you can see, you can try to see, notice all of that happening on the board. No less than you can notice a crab nebula and Ursa Major, a bear in the sky when you look at the constellations, right? So this game of life, designed by a mathematician, often comes up in discussions between evolutionary biologists or philosophers or other professions, because it's often used to demonstrate how very simple rules, as you have in this game, can account for incredible complexity, as you can see on this board. And that idea is important because it's often used in support of evolution, which also has very simple rules, but can account for incredible complexity and diversity on our planet. And the simple rules are of the evolution, obviously, random mutation and non-random survival of the fittest. So that's our natural selection, right? Well, this is kind of context of this famous Game of Life, but currently we are in a different context. We're in the context of lead code. This is a small coding problem. So within the context of this problem, we are offered to think of this game as a finite, predetermined grid size by m by n. So it's a matrix m by n of zeros and ones, where obviously ones represent live cells and zeros represent dead cells. That would be the current state of the board, right? So you can see something on the left. This is 4x3 matrix representing current state of the board as an example. And the idea is to transition this into the next generation, to transition every cell and therefore the entire board into the next generation and see which cells will stay alive and which will be dead. And transitioning into the next generation is governed by these four very simple rules. So instead of reading these rules, I'll probably give you this diagram that I've prepared. Okay, so these four rules say that the fate of the cell, whether it will live or die in the next generation, is heavily influenced by the number of neighbors the cell has. The number of neighbors. Now, each cell has 8 neighbors. Let's just be clear about which cells are considered neighbors. So if this is the original cell, then here will be its 8 neighbors. Okay, all of these cells around it are its 8 neighbors. And those 8 neighbors heavily influence or almost determine fully, most of the time, what happens to the cell, whether it will live or die in the next generation. And here is the rules. So almost any number of neighbors is fatal. If a cell has too few neighbors, 0 or 1, it will die as if from underpopulation. On the other hand, if a cell has too many neighbors, 4, 5, 6, 7, or 8, it will also die as if from overpopulation. Now, the only hope for a cell is to have 2 or 3 neighbors if it wants to live in the next generation. Now, having 2 neighbors is great because the cell can stay alive if it is alive, but a dead cell will obviously stay dead. However, having three living neighbors is really fantastic for a cell because it can come alive even if it's dead. If it's alive, it will stay alive. If it's dead, it will still come alive, as if in procreation or propagation or whatever you want to call it. But that's those 4 simple rules in a nutshell. So basically, almost any number of neighbors is deadly, is fatal, other than 2 and 3, and 3 is particularly great. So that's the whole idea of these 4 rules. And with these 4 rules, we have to determine what happens to the board. We have to remember that births and deaths occur simultaneously. Yeah, that's important. And that is kind of strangely very well explained in the first follow-up question, which says, you cannot update some cells first and then use their updated values to update other cells. That basically goes along with this sentence, which says that births and deaths should be thought of as if they occur simultaneously. Yeah. Now, about these 2 follow-up questions. The first one I'm going to address in the first part of the video. So that will be, this is how I'm going to be writing my code. The second follow-up I'm going to address in the second part of the video. That will be some additional, probably even substantial discussion. The first follow-up says, could you solve this problem in place? Now, I have to say, if you look at the function that they give us, you can see that they already kind of ask you to mutate the input. So board is the input, but there is no output. We don't return anything. This function is void, returns void. So we have to mutate the board. But in addition, they say, well, can you solve this in place? And what they mean by this is the following. So they say, don't do that, don't do this. So do not allocate a second matrix. So if this was our original matrix, yeah, so only 3 cells are alive, let's say, everything else is dead. Do not allocate a second matrix, a similar matrix, which you can think of as maybe next generation matrix, next generation. And then you can safely go through this next generation matrix in whatever order you want. And then for each cell, you want to look at its neighbors, right? It's 8 neighbors, but as they were in the current generation. So you could do that in the previous matrix, because previous matrix is not going to change. Because we're going to update this cell or any cell, this matrix will stay immutable. So we could easily do this in a new matrix, right? So once we do that, we could maybe just copy everything into our original matrix. Now, that would not be solving this problem in place. In place would be, do not allocate the second matrix. Okay? Just try to do everything in this original matrix. But that has certain challenges with it, right? If you're going through this matrix, in whichever order you're doing this, whichever order, you will have some of the cells already in the future state, but other cells in the past state. Until you finish the whole thing, you will have kind of mixed state. The matrix will be in the mixed state, right? And this is, as we can understand now, this can be a challenge, right? When you look at some cell and you want to determine its future state. So this is a cell in the past state, but some of its neighbors can be in the future state. For example, this cell, some of these neighbors, when you look at them, some of the neighbors could be, some of its 8 neighbors could be in the future state. So how do you know, how do you then deal with that sort of thing? Now, what I would suggest, therefore, is the following. I mean, transitioning cells into future state is terrible. Transitioning cells into future state has a problem because it will lose the past state. So why don't we, instead of transitioning cells into future state, why don't we transition them into some sort of dual state, which maintains the past state, but also somehow keeps the future state? So inside each cell, yeah, you know what? I'm going to have a larger cell. So imagine this large square is a single cell, as if we're looking with a magnifying glass. So we're looking with a magnifying glass at this little cell. That's a magnifying glass, and we see this image. Yeah. So this cell looks like this. And here we'll say we will keep the past state, and we'll also somehow put future state. We could use 2 bits. Yeah. So currently it's 0 and 1, right? A state. And that's a single bit. Why don't we make use of one more bit, a second least? So this is, let's say, the least significant bit takes care of the past state, and then a next bit, more significant bit, takes care of the future state. Yeah, we can do that. So this is what's going to happen then. So we probably have to go through this matrix not once, but twice now. The first time we go through this matrix, we're going to transition by the end, when we're done going through the matrix one time, every cell will be in this future past state. Let's call this dual state, right? So let's say, so initially, the matrix is in single past state. So it just past state. So it's some sort of classic state, let's say. Each cell just is 1 or 0 representing past state. Now, let's be this 0. After the first traversal, we will transition everything into some sort of dual state. Every cell will be in dual state. Okay? And then we're going to go through this matrix again, and from dual state, we're going to just transfer everything into the future state. Yeah? Now, this is a classic state. This is a classic state. This is a weird state that we just invented. Yeah? We called it every cell is in dual state. Every cell is in dual state. There is one complication here, though. I mean, this all sounds great. Yeah. Almost like we have a solution. Yeah, that kind of sounds great. However, there is a problem with this. One simple hiccup. So look at this dual state thing. Now, having dual state is great, but when we are in the middle of the first transition, we haven't really finished the dual state. So again, now, part of the matrix is still in the past state, just the simple past state, and the part of the matrix is already in the dual state. So some cells now say future past. Yeah, so some of them say future and past together. Right? So they use 2 bits to indicate future and past together. Yeah? Let's look at that closer. So when I am working on one of those cells, let's say I'm working on this cell. Now this cell is in the past territory, right? So now I have to transition this into this dual state. For that, I need to know whether it will live or not, right? So I'm going to look at 8 of its neighbors, And out of these 8 neighbors, I need to know which one was alive in the current generation. Now, some of them will be in past state, some of them will be in this dual state, and I need to always extract the past state from that, which is very easy. I mean, you see that we have, in both cases, the least significant bit is the past state, the least significant bit. Yeah, that's the crucial idea. The least significant bit, even in this mixed situation, when we have both past state and also the dual state, the least significant bit is the past state. I think now we're kind of ready to start implementing this. Is there anything else we need? Well, let's start implementing this and see. So first of all, as I traditionally do, I take this function that we have to complete and I move it over to typescriptlang.org, which has a playground, as you can see here. And this playground offers a slightly better editor than LeetCode does. Okay, so game of life. Now, first I'm going to implement some helper functions, right? So this dual state, right? Remember I said I need to be able to extract the least significant bit to determine whether a cell was alive, regardless whether the cell is in the past state or the future past state. I always need to be able to say, so was alive. That will be a function which will take the value of the cell, which in our case is 0 or 1, right? So we'll take that and return what? So it will say cell and so I'm gonna do this. What this is just number 1. This is binary. So 0b means binary and 0, 1 just means 1. So this is binary 1. And I'm using 0 in front of it because I just want to kind of indicate that this is, in my imagination, in my mind, this is a 2-bit bit mask, which masks the higher bit but keeps the lower bit. So it erases the second bit, right? I also will need maybe a symmetrical function, will be alive. Let me call it will live. So was alive and will live. And this will take the future state of the cell, So this can take, basically, we should probably say, this takes past or future past state of the cell. But the other one this only takes future past state of the cell. Obviously, you cannot just take past state of the cell on its own and return whether the cell will live or not. This is just converting from future past state into the future state, will live. So here I have to return what? Cell, binary mask, the mask with 1, 0, and then I have to, what? Right shift this one time. And what that means is just to kind of, so for example, if my future past state was 1, 1, if that was my future past state, meaning that was alive, that is our past, and it will live, that's our future. Now, when I apply 1, 0 as a bit mask, as a result, this will be erased, this will be turned into 0, but this bit will be carried over here. So that's 10 or 2 in binary 2. So this is binary 10, sorry. And then I need to shift this to the right, which will get rid of this 0 to get to this 1. Yeah. So that's what I'm doing here. Was alive and will live. Fantastic. What else do I need? You know what? Why don't I say a separate function constant count neighbors? That function will help instead of having that sophisticated, large piece of code inside here obscuring the simple logic that we're going to be doing inside. Why don't we extract this into a separate function? So this will be, you cannot just take Sal's value here to count neighbors, right? What I will need is the actual coordinates. So row, column, but also I'm going to take the actual board itself. Yeah. So that's the board, the matrix. And I'm going to count neighbors in here. Why I'm taking the board? I want to write a pure function. I do not want the board to be some sort of global or something. So I need to take the reference to the board, to the matrix. That's not going to cause copying anything. Remember, this is JavaScript. So how am I going to count neighbors? To count neighbors, I'm going to do, you know what I will do? Let's say this is my cell here. All of its neighbors have certain coordinates relative to the cell. So let me do them sparsely. So here are my 8 neighbors, right? Here are my 8 neighbors. So all of them have certain coordinates. So for example, this one is what? -1 in terms of row and -1 in terms of column. And this one would be +1 in terms of row and +1 in terms of column. So, you know what? I'm going to take an array of these coordinates. So this is an array. And the first pair of coordinates inside this array will be -1, -1. Then there will be -1 as a row and 0 the column. -1 +1. Right? Then the next row will be 0 -1. And then this is the cell itself. And then 0 +1. And then +1 -1. +1 as a row. 0 as a column. These are relative coordinates, right? +1 +1. Relative coordinates. Relative to this row and column inside this board. So relative to this row and column. Now let's map these. Let's map these pairs. Yeah. Let's map these pairs. So each pair of relative coordinates, let's map them to the actual board element, to the actual element of the board. Now remembering that some of these elements can actually be outside of the array, right? Because if row and column, for example, point to the left upper corner, then -1 -1 will be outside of the array. So potentially each one of these could be outside of the matrix. So remembering that, because TypeScript's not going to warn us about this. So remembering that, we're just going to map each one of these coordinates, each one of them, into the actual element from this board. How do we do that? So board row plus, we have to take delta row, delta column, and then row plus delta row, and then column plus delta column. Yeah. But what if this row doesn't exist, which could happen? If this, then it will be undefined. and then we'll try to access this element inside undefined, an error will be thrown. So we need this optional chaining, right? Now, if that row doesn't exist, then this whole thing will be short-circuited, this bit will be skipped, and this whole thing will return undefined. So this could be undefined. The other thing is, if this row does exist, but then what if this column inside that row doesn't exist? Then this thing will return undefined. So we can have undefined for two different reasons. Either the row doesn't exist or the column. Either way, we're going to take that undefined and convert it to 0. 0 means that cell is as good as dead. If it's outside of the board, we can think about it as dead. It will, in terms of counting neighbors, it will produce the same result as if that cell existed but was dead. Now, this element that we've kind of extracted, and maybe this 0, which simulates a dead cell outside of the board, we need to now decide whether this neighbor is alive or not, right? We need to count live neighbors. So why don't we apply this was alive function? Because this element could be one of those mixed, so it could be either in past state or future past. So if we apply this was alive function, then this function will correctly convert basically this element of the board into 0 or 1, to 0 or 1. So that will return a number. So now we have a number that is being returned by this guy. This returns a number, you can see. Now, how do we count neighbors now? Well, we should count how many ones we have in this array. So we took these array of coordinates and we mapped it into zeros and ones depending on which neighbor is alive. So now I need to just count ones. And to do that, I'll do a reduce and start with a 0. Okay, I'll start counting with a 0, and then total and alive. So this 0 will go into this total initially, and alive will be, whether the cell is alive or not, because the array is basically ones and zeros that we're reducing. So I should say total plus alive, and that is fine. Now I just have to return this. So I have to return this, and that will return number of neighbors. Yeah, I think that's fine. That's our number of neighbors. I think now we are ready to actually write our main function, game of life. And remember what we have to do. We have to go twice. We have to do 2 traversals. Yeah. The first time we do traversal, we convert every cell into this dual state cell. Okay, we convert everything into the dual state by saying 2 bits. First bit will be future, the higher, more significant bit, and then least significant bit is past. That's what we have to do with every cell. Let's do that. So for let row equals 0, row is less than board length, plus row. That's going to take us through all the rows. Now, columns, let column equals 0, column is less than board row dot length. That will take us through the elements of that particular row, and then plus column. Now, we are looking at a specific cell called board row column. And this is its past state. This is the past state, definitely, because we haven't really converted this yet into the future past. But the neighbors could be in the past state or future state, but we don't care because we can quickly calculate, we can quickly count neighbors with our function count neighbors, yeah, which will take row, column, and the board, and it will count neighbors correctly, regardless of what state the neighbors are in, just past or future past. Now that we know neighbors, what will be the future state, future past state? So let's decide first whether the cell will live or not. Constant, well, will live in this function, which I don't want to overshadow that thing. Neighbors, future state will be. Now, to determine the future state, we need these simple rules of our game of life. These rules, yeah. So that basically says the only hope for a cell to be alive is this: having 2 neighbors or 3, and having 3 neighbors is particularly great because if a cell has 3 neighbors, it's guaranteed to be alive. Yeah, let's write that. So having neighbors equals exactly 3, that's guaranteed to make you alive. Or the only other chance is having 2 neighbors, but also you have to be alive at the moment. So having 2 neighbors and it has to be alive itself. But we know that we don't have to apply was alive to this particular cell. Why? Because we know it's in the past state. So we don't have to extract anything. It is already in the past state. Now remember, and is more powerful bond than or. So basically this is equivalent to having this in the parentheses. Yeah. That means that's correctly going to give us a Boolean or sometimes a number, because this is a number. The way JavaScript evaluates this is you could end up with this value, right? So if this is false, then this will be evaluated. And then if this is true, this will be evaluated and this will be the result. In every other case, this will be Boolean, right? So that's why we have Boolean or number. Yeah. Why don't we just, you know what, tell JavaScript that this is a number? Because, and you see, it doesn't really complain. If I were to say this is a string, it would probably complain, yeah? But I'm saying it's a number. Well, because it knows Boolean and number are the same thing under the curtain, so it says, okay, you probably know what you're doing, yeah? Which hopefully we do what we're doing. This is going to be number or Boolean, but either way, it's going to be 0 or 1 every time. So I'm just going to say, well, we're going to treat this as a number. Okay. Now we can calculate the new value of board row column. And what it's going to be, we're just going to prepend it with what? With future state, but it will be, we're going to left shift it once, yeah, and then add it to this. And that will be our new value of this particular cell. I hope that makes sense. And that finishes the first traversal. The second traversal will be, let me just copy these. So the second traversal should be simpler. The second time we go through our array, now everything is in this dual state. Every cell now is in dual state, which is future past. And we just have to extract the future state for each cell. So for each board row column, we have to say equals to will live. Remember, we created a special function, will live, that extracts the future state from this. So we have to apply will live to a cell, to the value of a cell, and then write it back into here. And that's it. That should be it. Now we're going to try to copy this to LeetCode, back to LeetCode. Let's go back to LeetCode. Yeah. Paste it. And I'm going to run it on pretests. and see what happens. Okay, both pretests passed. Now I'm going to submit it, but I do not expect this to be very fast. I mean, I expect it to be, actually, performance will be very slow, I would say. Why? Because, I mean, it's not that complexity is bad or anything, not because of that. The problem here is that we here prioritized readability over speed, right? So, for example, I mean, I'm calling functions to do the map here. I'm calling functions all the time, and the reduce is going to call this function all the time. And here as well, I have this will live as a function being called from there. And all the time, I mean, I'm just... so this may be improving readability, but calling functions is costly. Even though these are arrow functions, which is faster than normal functions, still this is costly. It's not important, though. This is not... It's not that it's the time complexity here is poor. This is decently efficient code. It's just it's not optimized for speed. And for this particular problem, I think this is what I chose. I think that's just probably a good decision. Okay, let's submit it and see what happens. So anyway, I do not expect it to be particularly quick. Okay, so we got accepted. 4 milliseconds, which is a lot for this small boards. I mean, our board size is very small, as I remember. Right, M and N, width and height are both maximum 25. So we only beat 17% of code in terms of speed. In terms of memory, we did slightly better, but not much. So anyway, this was accepted, and this is fine. Let's now talk about that follow-up question. So remember we said there were two follow-ups. The first one, we already did it. It was asking about doing this problem in place. We did that. Now the second question. The second one talks about trying to make this board infinite. Let me just read the question. In this question, we represent, well, in this problem, we represent the board using a two-dimensional array. In principle, though, the board is infinite, which would cause problems when the active area encroaches upon the border of the array. It does live cells reach the border. How would you address these problems? So basically, how would you address the problem of trying to represent an infinitely sized Conway's game of life, the board? Now, they can't really seriously ask us, obviously, to represent an infinite board in the sense that this game can grow infinitely and there could be infinitely many live cells at some, well, not at a given point, but the number of live cells can grow infinitely. So that cannot be the meaning of this question. What they really mean is the following. Let's say we have a manageable number of living cells. And this is kind of already can be seen from, they're talking about when live cells reach the border. So they care about live cells, right, somehow, which is kind of understandable. So let's say we have a couple of live cells. Yeah, say this cell and this cell. These are only two live cells we have, but they're very far away from each other. The distances are huge. Let's say this has coordinate 0, 0, and this has some huge coordinate size. I don't know. I don't even know what these numbers are. 10 to the power of 18 row and 10 to the power of 18 column. So some huge. Why don't I just add, instead of 18, 10 to the power of, I don't want to make it even bigger that I cannot easily represent. Well, I could easily represent them as big integers in JavaScript, right? Anyway, this is enough to make a point that we could have a manageable number of living cells, but basically the distances between them are huge. At least the largest distance between the two points that are furthest away, these are huge. So if you wanted to represent them in a matrix, you would need a really big lot of memory to do that. Can we represent that sort of thing efficiently? Now, to do that, there are a number of ways of doing this, right? As always. Now, I would propose something that I feel comfortable with. So let's say I have 3 rows: row with index 7, 12, and 35. Okay. Now, I only want to allocate memory for these rows. I do not want to allocate memory for all of the rows in between. And to do that, I can use map. Yeah, the structure in JavaScript that does that is a map. So why don't I try to use a map? And I'm going to map what? I'm going to map each row, index of the row, so a number. Yeah, I'm going to map each number to some sort of row. And the question would be, what's that row? Yeah, some kind of structure that I will use to represent a row. So what's that row? Now, the row could potentially be an array, not great, because it could also have just a couple of elements, say, for example, minus 17 column and plus 321. Yeah, so I don't want to allocate the entire array. What I want to do is allocate just small kind of cells here. Now, I could also use a map here as well. So row could also be a map. So each column index could be mapped to some sort of number that you want to put here, 0 or 1 or anything else, 17 or one of those 2-bit numbers that we set, so binary 11, for example, which has past and future state. But you know what? I'm just going to do booleans. So 1 and 0. 1 and 0 is fine. But if I just need 1 and 0, then I don't need really a map. A set would also be fine, right? So row could be represented as, I could represent a row as a set. And set will simply contain only those columns that are alive in this row. So set of what? Set of numbers. And these are column indices. That is my memory structure. That is the structure that I'm going to use, a container that I'm going to use to represent the board. And that will be pretty decent. Now, a small warning, something that we cannot do here. Yeah. So for example, I cannot have a board represented like this. Board equals new set of, let's say, a row number, column number. Yeah, that cannot be, that will not work. Okay. Because let's say if I add board add row 1, column 7. Okay, I've done this. Now, if I ask this board, do you have this element, row 1, column 7? We would expect the answer true, but instead we're going to get false, even though we've just added this element. But if we know JavaScript well, we know that we didn't really add this element. We added a similar looking object inside the board, but it's a different object, right? This object is not the same as this object. It's different. So, for example, number 5 and another number 5 are exactly the same numbers, but in terms of objects, they live in different spots of memory, and therefore they are different objects, right? So, for example, if I change row here to 5, I mean, have I changed it in both objects? No, not really. So these are both different objects. Yeah, and you can try this actually. let's say if I were to console log this, yeah, I would actually, let me open, I would actually, if I run this, I would get false. Yeah, let's run it again. I get false. The only way I would get true is if I created some sort of object and this guy was this object, and now I say add object, and I could now say, well, do you have the same object? Now this is true. Okay, but this is useless because I can't remember references to those objects outside of my set in order for me to be just query the set. That's impractical. That's impossible. Then why do I even need this set? So I cannot use that sort of structure. What I need to use is whatever we just talked about. And this is this sort of map, which maps index of the row to set of columns, set of numbers. So let's do that. Create a class Conway game. And the first thing it's going to have that board. Private read-only board equals new map of numbers to set of numbers. Okay, beautiful. Now, public read-only is alive. So we're going to query if some sort of row column is alive. And we're going to return this board get row. So I'm going to get a row from this board, and it's going to be either undefined or actual row. Now, if it is undefined, I'm going to use this optional chaining. But if it's defined, then I'm going to just say, well, if it's defined, it's a set. If it is defined, then it's this set right here. And set, I can ask, has col. Does it have this column? That would be a Boolean, which I will return. But what if this thing is undefined? Then this whole thing will be undefined. So I have to convert this to false. Undefined means false, right? That row doesn't exist. That means, well, the cell in that row cannot be alive if it's if the row is not there. Because as you remember, we store all the living cells. Anything that we do not store, anything we ignored, only dead cells. Another one, public read-only set alive equals row number, column number. So I'm going to set a column alive. How? Constant r equals this board get row. Again, this is either undefined or a set of numbers. Yeah, set of numbers are undefined. So if this exists, that means it's a set of numbers. It's a row. Then to that row, I have to add col. Otherwise, well, otherwise means the row doesn't exist inside our board. This board has no row for this row and column. So I have to create it. This board set row. So I'm going to set, and this is a map. So I'm going to map this row to a set, to a new set, which going to have a single element, and that single element going to be this column. Yeah. So that will set that row and column alive. We're going to set this alive. Okay, let's fold these. Now, these are very basic implementations, obviously. Very basic. You can have various different other important things there. Maybe check whether this is already alive before you set it alive. Maybe return false. Just whatever you want. But this is very basic just to help us solve this problem with an infinite board. What else do I need? Is alive, set alive. How about a constructor? How about a constructor? And why I need a constructor is because potentially I want to pass in a board, which is number, yeah? Because we just said we're going to use this to solve this problem. And in this problem, we are given an array. Oh my God. We're given an array. Remember, how was it? Like this, a matrix, not some sort of map of sets. And so I should be able to take that and import it. And to do that, in the constructor, I do not want some complex logic. Let me just do private read-only import. And this will be, it takes board number. Now, this here could be optional. Let's make it optional. But here in import, this will not be optional. What I will do here is I will go through board for each. So row and row index. And for row, for each element, col and column index, I'm going to do what? Sorry. One extra parenthesis here. So what am I going to do? If column exists, if it's truthy, that means that cell is alive. And this column is actually a cell. Yeah, because column inside the row, this is a single cell. So the value of this cell, if it's truthy, then the second part will be evaluated in JavaScript. And here I will say this set alive, row index, column index. Yeah, beautiful. So now I can say here, if board exists, then why don't you do this import board? Great. But I want to foresee a different way. So let's say I already have a board. I have a Conway game, which has this board in that format. What if I want to kind of clone this? So why don't I also say, or I want this also to be passed into the constructor. Now, this will be if array is array board, then that. Otherwise, else if board instance of map, then what? Then I'm going to shallow clone this. I mean, this is not great, but for this problem, this is fine. This board, I'm going to reassign this board. So initially it will be this empty map, but I'm going to quickly reassign this. This will be shallow clone very fast. This board, a new map of board. So what that means is this is a map of rows, right? Each number is mapped to a row. So this shallow clone will reuse these rows. So it will be the same rows, a different map object, but the same rows inside. That's important. So technically, this is a dangerous point if you're going to release it like this inside the nature. Somebody's going to get into some sort of trouble with that sort of thing. But we're not releasing this anywhere. This is just for lead code. Yeah? So this is fine for now. So I have this constructor. Beautiful. Why don't I now start working on public read-only next? This is the next generation. Move to next generation or time tick or something. So next generation. No parameters. It's going to do. So here's what I'm going to do here. So first of all, I'm not going to do this in place because I'm using a set, which is basically kind of a Boolean. So for each cell, whether this cell actually exists, that's stored by the fact that this column is there. So there is not much more room to store there. So basically, I don't have to solve this in place. I mean, this is quite memory efficient. I can duplicate it. So I can say constant old board equals new Conway game. And Conway game is the class that I'm writing right now. So I'm in the middle of writing that class. And I'm saying, well, in the middle of writing this class, I'm going to actually use this class, which is fine in TypeScript. This can happen. But I'm going to clone this board. I'm going to clone this board. The board that this current instance of current Conway game has. I'm going to clone this. Now, potentially, here is that dangerous situation, right? Because now the instant that I'm working inside and this old board, they reference the same rows. But I'm going to release these rows because I'm going to have public read-only clear, which is a function that just clears the board. Yeah. And import. You know what? Inside the import, I'm going to say clear equals true. And I'm going to say if clear, then this clear. Yeah. So import, if you want to use it, if it's public, then you may want to clear it. Initially in the constructor, there is no need to clear it. Or is that? This board false. Okay. Now, I'm just trying to conserve space. I'm using large font, so white space is at premium here. So again, I create a new class which will share rows with me, but I'm just going to release these rows. So I'm not going to reference them anymore. I'm going to release the rows. So this old board can take those rows and consider them to be its private rows because I've just released them. Okay. Now what should I do? Well, now I'm just gonna, well, remember we have these living cells, so I can go through all of them and look at each of them and decide whether they're going to live or die. But here's a problem. I mean, how about neighbors? I mean, if these are living cells, unlike the matrix, we are only going to visit the living cells if we go through this container because we're not storing dead cells anymore. But do dead cells have a chance to come alive? Well, yeah. For example, this cell, if it had three living neighbors, if it had exactly 3 living neighbors, this guy has a chance to come alive, right? So I have to examine some of the dead cells as well. Which are these? Well, one thing is, if I were to examine all of the 8 neighbors of all of the existing ones, all of the 8 neighbors of every cell, yeah? Well, the cells themselves too, the cells themselves as well, but also their existing 8 neighbors. If I did that, so all of the existing 8 neighbors, well, that would be a lot of overlap, right? So I could be looking at this cell multiple times and trying to see whether it will live or not, which isn't too complicated, to be honest, because I can, no, because if it's dead, if I haven't edited it, I will not know whether I've already addressed this neighbor or not, right? So you know what? Why don't I create another map? In that map, I will just say, I will just put all of these cells themselves and also their neighbors. And some of them, this structure, a similar structure like this, it will not contain duplicates. So each cell, I can put them multiple times. I can put, this neighbor could be a neighbor of many different cells, right? So it's also a neighbor of this guy, and also this guy, and this guy, and this guy. So this can be put many, many times in here, well, 8 times maximum, but it will eventually end up here being once when I try to query it. That sounds like a good idea. But instead of doing this, I mean, I already have this structure. So with all of the logic, how to add them inside. So you know what I'm going to do? I'm going to create candidates. But candidates will be new Conway game. So candidates will be an empty new Conway game, brand new Conway game with a board like this and with logic that is set alive. I have set alive logic and is alive logic. So I'm going to reuse that. So again, I'm inside writing this method next inside Conway game. I'm using this Conway game inside itself already second time. Okay, so now what I should do is go through old board, because my own board is being cleared. So I should go through the old board. So let's take old board, which has board, that thing, that structure. So old board has that board, and I should go, how should I, let's do for constant of, and I'm going to do what? The first element going to be row index, because it's a map. So it's going to be the key, which is a row index, and then the actual row, which I kind of represent with single letter, right? Up there somewhere. I already used that. Where was it? Where was it, buddy? It was, for example, here, right? So I'm going through this. I'm going through this board, which is a map. And this will be key and value. This R is a set of numbers, right? Remember, set of numbers. And this RI is the index. This is a row index. Now I'm going to go through this. This is a set of numbers, right? So for constant column index of R, yeah. So again, set of numbers, and that's that number, which for us means column index. Now I'm going to take this row index and column index and put it inside candidates, and also it's 8 neighbors. So I would say, I don't have to check whether it's alive or not, because I'm going through the board, which only contains a live element. So I can say candidates set alive. Remember, candidates is actually a Conway game. So I can just say candidates set alive, row index, column index. I can just say that. And also I need these 8 neighbors. Now I'm going to write private get neighbors function, neighbors function, for row and column. And here I'm going to return, let's take this, the relative coordinates. I'm going to return absolute coordinates. But here I'm just going to start with relative coordinates. But I need to now convert them to absolute coordinates because they're relative to this row and column. So why don't I do map, and each element will be this tuple. So deconstruct this tuple, delta row, delta column, and let's say return what? Row plus delta row, column plus delta column. Yeah, so get neighbors will return these tuples. Although, you know what, I'm going to say sconst, so that this now will say this is actually a tuple and an array of tuples. This read-only, that's fine. I mean, I could just do it differently. Maybe, let's say, number. Yeah. So that will also produce the same result. Yeah. Maybe this is better. Fine. Yeah, that sconst is a shorthand solution for those sort of things. So I have get neighbors. Remember, I need to add get neighbors into candidates, all of those 8 neighbors. So why don't I take this get neighbors? Why this? I mean, I could also do it on candidate itself. So candidate get neighbors, same thing. RICI, get neighbors. And then this is basically an array of tuples. So for each, and let's deconstruct the tuple into row index, column index, although I'm using row index, column index. So what should I say? Row index, column index, row J, column J. I mean, I could have easily used I could have easily overshadowed it, no problem, but let's do it that way. So row J, column J, and what? Candidates dot set alive, row J, column J. Hopefully let me not make any mistakes. So candidates get neighbors. Doesn't matter what I say. It could be this or old board, anything. Doesn't matter here. Get neighbors. I'm going to reference the same get neighbors function anyway. RICI, which is correct because this is the current element that I'm looking at, the current alive element. And then I'm going to say for each of the neighbor coordinates, candidates, I'm going to set this, now it matters. I'm going to put it inside candidates. Candidates set alive. So I'm not really setting this alive. I'm saying this is going to be a candidate. This may be alive in the next generation. Okay. All right, so I have that. I went through all the, I've populated candidates. Now what I should do is go through those candidates. Yeah. And to go through those candidates, why don't I do the same thing? Just candidates. And inside this loop, while I'm going through the candidates, I'm going to say so this is row index and column index will be the index of the candidate. Now I should look inside old board, right? And if it, I don't have that function. If it will live, RICI, if it will live inside old board, yeah, if I have to write this will live function. If it will live, then what should I do? I should do in this set alive RICI. That's what I should do, right? If old board reports that this row and index will live, there is nothing else that may be alive because all of the candidates are now in the candidates and I'm going through all of them and I'm asking old board, hey old board, will this live in the next generation? If it yes, then I've cleared my board so that I can only put indices of all of those cells that will live into the next generation. That makes sense. I just need this will live. So let's write will live. Let's make it public, read-only, will live. And that is what? It takes row and column, right? And returns what? It returns, first of all, it needs to count neighbors. Oh, we need public, read-only, live, let's get live neighbors. That is what? Live neighbors. Row, column. I need to count live neighbors. To count live neighbors, why don't I get neighbors? Yeah. Let's take constant neighbors. You know what? Just return. Sorry. This get neighbors of row and column. So this will return all of the absolute coordinates of all of the 8 neighbors. Yeah. So this is an array of tuples. I want to map this to what? So let's deconstruct that array of tuples. So row index, column index. And let's say this so all of these neighbors, we should say this is alive, this row index, column index. Now, an array of tuples will be mapped to an array of booleans because this is boolean. For each coordinates, this is a boolean. Now I just have to count how many true I have. Let's reduce that. You know what? Why don't I just convert it to a number so that TypeScript understands that this is actually that this map actually returns a number. If I was in JavaScript, which I kind of am, TypeScript is the same as JavaScript, I wouldn't even do this. I wouldn't bother, but it's hard to kind of sometimes convince JavaScript, TypeScript that Booleans are also very similar to numbers. They behave in some sense, but I think TypeScript is correct because they don't always behave the same way, unlike, say, C++ or something. So I just have to count ones now. And to count ones, I'll just have to sum everything up. So start with a 0, and let's say total and what else? Alive. And I'm going to say total plus alive. What's going on? Oh, because alive is so. Yep. So what happens is 0, the type of the 0 was just 0. Okay, so total was, what was the type of total like that? It's just 1 or 0. Clever. But total plus alive is no longer assignable back to total. Yeah, because it could. So, okay, I just have to broaden the type of the 0 and say, well, you know what? 0, but treat it as a number, not just a 0 or 1. TypeScript is very clever, but sometimes being very clever means a lot of nuisance. But fine, I mean, this unusual weird thing is the short, simple solution for that particular problem. Now we have, what the hell did I do? We have these live neighbors, which counts live neighbors. Now I can write will live. Will live would be what? Return. You know what? Let's count neighbors. Constant neighbors. Neighborhood. Where the hell did that come from? Neighbors. Where is it from? Neighbor. Neighbors equals this live neighbors of row column. Now I'm going to return to calculate whether a cell is alive or not. Neighbors is exactly 3, or neighbors is exactly 2, and what? This is a live row column. Yep. So if you have 3 neighbors, the cell is going to stay alive. The cell will definitely be alive. Or if it has 2 neighbors, but in this case, it must currently be alive. That's correct. Yeah. And I think now this is done. Is it done? I forgot what I did. And so, yeah, this is beautiful. Let's fold next. So this class seems ready. Is it ready? Well, not really. We need an export. So we have import. Why don't I have export? Public read-only export. And let's take min row number, max row number, min column number, max column number. Yeah. So I'm going to create a board, which will be, type will be, it's a matrix. I'll set it to an empty matrix. No rows, no columns. More importantly is that there is no rows, because this board is actually an array of rows, and it's empty because it has no rows. Now, let's go for, I could potentially create array from. I could actually create that array to allocate it properly. Length would be what? I have max row minus min row plus 1. Yeah. And then for each row, I will map it into, let's say, new array. How many elements? Max col minus min col. Max row, min row. Oh, that would have been a problem. Maximum column minus minimum column. And I don't need to fill it with anything, but okay, let's fill it with zeros. But technically, that's not necessary because I'm going to assign values into them. This is a really horrible. Let's just make it an empty thing. I mean, okay, for let row equals min row. Row is less or equal to max row. And plus plus row. Or let column equal min column. Column less or equal to max column. Plus plus, oops, plus plus column. So here I would create constant let row, let constant r equals an empty row, which is, and I can instantly say board push r. Here I would say board, no, row with index column equals what? I'm exporting. This is alive, row column. Hopefully I'm not making a mistake here. Boolean is not assignable to number. Yeah. So row is going there, and then column. So this row column R, which is this, and I've pushed it. Okay, this sounds fine. This basically exports some sort of snapshot, a window of this infinite board. It would also be great to maintain somehow to keep the minimum, the actual, the smallest window that contains all of the living cells. But that we don't really need this, and this could be a little bit tricky. So I'm not going to do it here. Do I have everything? Yeah. So now why don't I write a small adapter type of thing? Remember the way we have to deal with this is we have to have that sort of function. Game of life. This is what lead codes wants, right? So I am going to write this function in this way. So we have this board. Let's create constant game equals Conway game from this board. And we can do that, new Conway game. We can do that because we have a constructor that can deal with this. Now game next, as easy as that. Now we have to export constant result equals, and we can say game export, and we should say what size, because potentially the board could have grown. So why don't we say constant height and width equals board length, board 0 length. If board length is 0, then this will be undefined, dot length will be an error. So if no board length, just return, nothing to do. Otherwise, I'm working on result. So result would be min row, max row, right? Min row 0, max row is height minus 1. Min column 0, max column width minus 1. Now I have to mutate this board, basically take this result and somehow replace everything that's in board with this stuff. So what should I do? So result is just an array of rows. So I can reuse those rows from the result. Yeah. And I can say, so board splice, get rid of everything from 0 to infinity. Every element will be, or in this case, every row, each element of the board is a row. So I'm going to get rid of every element. And I'm going to replace them with the rows from the result. Result. Why? It's a void. Game export. Oh. Game export. What is export? Export, import, export. This should return. See, that's the beauty of TypeScript. I forgot to say export board. Sorry, return board. And I got red squiggles here. And they're now gone. Board splice this. Now, I could replace this result with this thing. So like this. Yeah. Which would be great because now I won't have any other reference to this. Otherwise, now this result and this board both have the same rows actually, which is kind of unpleasant. So technically, this would be better. It doesn't really look great though, but let me keep it like this. Okay, copy. I think this is ready. I can paste this now into lead code. And to be honest, I probably made so many typos in there. Let me just submit this to pretests. My God, there's going to be so many errors in. Oh, wow. Okay, that's very lucky. Oh, where is the submit? Let me. Yeah, okay, this is submit. So let me submit on the actual. It's going to be very slow. Even if it passes, it's going to be extremely slow. Very slow. Very, very slow. Yes, I think it's probably somewhere with the slowest potential solutions, this one, because it's not surprising. I mean, we are doing these horrible things. We're converting this into some sort of class which can deal with infinite boards, and it's got maps and sets and God knows what. But this could deal with, well, the class could deal with an infinite board, this class, in that sense that we discussed, yeah? Okay, so that was a discussion of Conway's Game of Life, which is a fantastic concept. It's a wonderful concept. It's a very interesting concept. And, you know, I felt excited and honored to kind of play with this thing. I've never really implemented Game of Life. So it was really nice. It was very good.